welcome to the lecture titled Identification of Underdamped Systems. Lots of systems, subsystems, processes, components and devices in industries are found to possess underdamped characteristics. That is why there is the need for delivering a separate lecture on identification of underdamped systems. How can we represent the dynamics of an underdamped system? Often it is given in the form of a transfer function model H G s is equal to k dash e to the power minus theta s upon a dash s square plus b dash s plus c, which again can be converted to the form of k e to the power minus theta s upon a s square plus b s plus 1, assuming k is equal to k dash by c, a is equal to a dash by c and b is equal to b dash by c. Why we express the transfer function model in this form? Because earlier we have found the transfer function models in this typical form. That is why allow me to express the transfer function model in this form, where the last term of the denominator is having 1. Please keep in mind the term in the denominator is having 1 in it. So, to obtain similar type of transfer function model, allow me to assume k, a and b in this form, that enables me to write the transfer function model H G s is equal to k e to the power minus theta s upon a s square plus b s plus 1. Now, with various values of c, if I choose c equal to 0, then what happens? Then the denominator, this term will be 0, resulting in a transfer function model known as an integrating model or the transfer function for an integrating process. Okay. So, also when I choose c as negative value or positive value depending on the value of c, it is possible to express the second order plant model as the model for an unstable or for a stable process. Okay. So, those things are very easy that you can easily make out. Now, when the second order plant model is given in this form and when further assumption like b square minus 4 a c is less than 0 is met, then only this transfer function model or plant model transfer function is said to have underdamped characteristics. Please keep in mind, only when b square minus 4 a c is less than 0, then only the plant model becomes a plant model for an underdamped system, otherwise it is not. So, I will go ahead with the further analysis. The generality of the transfer function model can be explained by this fact that when G s is given in the form of k e to the power minus theta s upon a s square plus b s plus 1 and various values of c are chosen when c equal to 0. We do not see c here, but as you know k is equal to k dash by c, a is equal to a dash by c and b is equal to b dash by c. So, c is inherent in this in these coefficients. Now, when c equal to 0, it is possible to get G s expressed as some form which will give you the transfer function model for an integrating process given as k dash e to the power minus theta s a dash s square plus b dash s. Okay. Now, when c assumes negative value c equal to minus 1, similarly, I can get a minus 1 here. When c equal to plus 1, I get here plus 1. So, that is how we get a variety of transfer function models from this general transfer function model. That is why I say that this G s possesses some generality. Now, what benefit you get from this? That whatever expressions we will discuss can easily be extended for identifying a varieties of process dynamics. The process can possess integrating characteristics, can possess unstable dynamics, still the equations can be employed to find different type of transfer function. Now, we will assume that the relay in the relay control or closed loop system is an ideal relay. So, the relay characteristics will be given by H and minus H. Okay. Then the output of the relay control system will be symmetrical outputs. Okay. So, for this analysis particularly we will not assume or take any asymmetrical relay, rather a symmetrical relay will be considered for each in analysis of this underdamped systems. Now, when the denominator polynomial is considered, what is the denominator polynomial? That is a square plus b s plus 1, this is the denominator polynomial. This can be expressed further as a times a square plus b by a s plus 1 upon a. Now, this can further be expressed as a times s minus gamma 1 minus j gamma 2 times s minus gamma 1 plus j gamma 2. I can always factorize this in this form, because using the roots of the denominator polynomial given by gamma 1 plus j gamma 2 is equal to minus b upon 2 a plus j times root of 4 a minus b square upon 2 a. This is the way we find the root of a characteristic equation. So, the first root is like this, then its conjugate can be given in the form of gamma 1 minus j gamma 2 is equal to minus b upon 2 a minus j root of 4 a minus b square upon 2 a. So, when the two roots are assumed in this form and subsequently when you allow me to write the roots in the form of some variable lambda 1 is equal to gamma 1 plus j gamma 2 and lambda 2 is equal to gamma 1 minus j gamma 2, then the polynomial can further be written in the form of a s minus gamma 1 s minus lambda 1 times s minus lambda 2. So, there are various ways the polynomial can be expressed. Now, why we are doing this? So that the state space equation of the dynamics second order underdamped system model can be obtained easily. When the polynomial is available in this form, it is very easy to find the state space representation of the dynamics. Okay. Now, the roots of the denominator polynomial I have already given. Now, allow me to write the transfer function now, G s, which is nothing but k e to the power minus theta s upon a square plus b s plus 1 can also be written in the form of k divided by a times e to the power minus theta s. In the denominator we will have s square plus b by a s plus 1 upon a. Okay. By writing so, what do we get? What is y s? What is g s? G s is nothing but y s upon u s. The process ratio of the Laplace transform of the process output to the process input is given as now k by a times e to the power minus theta s upon s square plus b by a s plus 1 by a. Why we are doing so? To find the state space representation for the dynamics. Okay. Why it is again important for us? Unless we find the state space representation, then we may not be able to develop or describe the relevant expressions necessary to identify the model parameters of an underdamped second order plus dead time dynamics. Now, again this can be written further in the form of y s upon u s e to the power minus theta s is equal to k divided by a a square plus b by a s plus 1 by a. Now, already we have introduced lambda 1 and lambda 2. What is lambda 1? Lambda 1 is equal to gamma 1 plus j gamma 2 and lambda 2 is equal to gamma 1 minus j gamma 2, where gamma 1 is equal to how much? Minus b by 2 a and gamma 2 is equal to 4 a minus b square root by 2 a. Okay? These things already I have explained. So, when these things are used here, I can write b by a and these forms in the form of lambda 1 plus lambda 2 will be equal to now gamma 1 2 gamma 1. So, 2 gamma 1 is nothing but yes. So, gamma 1 is this one. So, 2 gamma 1 will be minus b by a. Similarly, lambda 1 times lambda 2 will be equal to gamma 1 square then plus gamma 2 square. Okay? Multiply the two lambdas, lambda 1 and lambda 2, then you will get gamma 1 square plus gamma 2 square, which will give us b square by 4 a square, again plus 4 a minus b square upon 4 a square, giving ultimately 4 a upon 4 a square, which is nothing but 1 upon a. So, I can write the denominator now in the form of either b by a or 1 by a, or I mean now the same expression can be rewritten as y s upon u s times e to the power minus theta s is equal to k times lambda 1 lambda 2 in the numerator. Please keep in mind 1 upon a is equal to lambda 1 lambda 2. Therefore, I can write k divided by a as k lambda 1 lambda 2. Similarly, in the denominator I get a square plus, I have got this one. So, I will get minus here. So, a square minus lambda 1 plus lambda 2 times s plus lambda 1 lambda 2. So, basically what you have got now? K lambda 1 lambda 2 divided by s minus lambda 1 times s minus lambda 2. Okay. So, this is how we get the transfer function expressed in this form. Now, this transfer function can further be written in the form of this. I will rewrite this, derive the state equation using the basic principles. So, using the basic principle, how can we obtain the transfer function state space representation of the underdamped process dynamics. Now, then cross multiply and take inverse Laplace transform, that will give us, if I cross multiply these terms like this, then I will get this as y double dot minus lambda 1 plus lambda 2 times y dot plus lambda 1 lambda 2 y is equal to k lambda 1 lambda 2 u t minus theta. Okay. So, this is the linear equation we have got, the differential equation we have got for the dynamics of the underdamped plant. Okay. Now, let me introduce the state variables. Let x 2 equal to y and x 1 equal to x 2 dot first order derivative of x 2 is equal to y dot. That enables me to write this in the form of state variable as x 1 dot minus lambda 1 plus lambda 2 x 1 plus lambda 1 lambda 2 x 2 is equal to is equal to k times lambda 1 lambda 2 u t minus theta. Now, let this be equation number 1 and this be 2. 1 and 2 can be used to get the state equation now. So, allow me to write that further, x 1 dot x 2 dot is equal to now x 1 x 2 plus for the input that will have u t minus theta. So, this is the way one can write the state equation. Now, x 1 dot has got lambda 1 plus lambda 2 here times x 1, then lambda 1 lambda 2 here, then I have got k lambda 1 lambda 2. Okay. And what about the x 2 dot? X 2 dot is equal to x 1 only, therefore, 1 it will be 0 and it will be 0. This is how we develop the state equation for the underdamped dynamics. Okay. And the output equation can be given outright in the form of y equal to c x h 0 1 x 1 x 2. So, when you multiply, you ultimately get y equal to x 2, and that is what we have assumed earlier. So, we have introduced the state variable x 2 as y. So, this is how we develop the state equations, and then the state equation constants now are the A matrix is given by this, the B vector or matrix is given by this, and the C is given by this. So, that is what we have got here. So, A can be the A matrix corresponding to the state equation can be given by lambda 1 plus lambda 2 minus lambda 1 lambda 2, sorry, I have, if I take this to this side it will be minus, sorry, obviously because x 1 dot is equal to lambda 1 plus lambda 2 x 2 minus lambda 1 lambda 2 x 2. Okay. So, this way we will get this minus. So, that is how the A constant is found to be having components or elements lambda 1 plus lambda 2 minus lambda 1 lambda 2 1 0, and that is what we have obtained lambda 1 plus lambda 2 minus lambda 1 lambda 2 1 0. And similarly, the B matrix is having elements k lambda 1 lambda 2 and 0. Thus, it has got k lambda 1 lambda 2 and 0, and C is given by 0 1, C is given by 0 1. So, why I am doing all these analysis? When we get the state and output equation expressed in some convenient form, the set of powerful equations we have derived earlier for identification of second order plus date time transfer functions or transfer function models can easily be extended to the underdamped second order plus date time dynamics. Okay. So, the earlier we had got for the earlier cases for the second order plus date time system transfer function models, what were our A? A was lambda 1 0 0 lambda 2, if you recall this, then B was equal to 1 1 and C will having some different form, there were 2 elements. Okay. These were the form. Now, in place of the standard A, B, C forms we have been using during last few lectures, allow me to get the A, B, C in this form for identification of underdamped systems. Now, A is having the elements given in this form non-diagonal form, and there is no problem, it is not absolutely not necessary to find A, B, C constants in diagonal or some other form, it could be available in any form. Okay. Now, when A, B, C are found in this fashion, then subsequently we can make use of these constants and the state and output equation for deriving analytical expressions necessary for identification of the parameters of the second order plus date time model. Let me repeat how we have been able to find the state equations which has got constants A, B and C given G s in the form of k e to the power minus theta s, A s square plus B s plus 1, when lambda 1 is equal to gamma 1 plus j gamma 2 is equal to minus b upon 2 a plus root of 4a minus b square by 2a, and lambda 2 is equal to gamma 1 minus j gamma 2 is equal to minus b upon 2a minus j root of 4a minus b square by 2a. This j you should not forget, because we know that for underdamped dynamics, b square is less than 4a, b square is less than 4a. Therefore, 4a minus b square will be positive, and therefore, j will appear over here. Or if you use, when this is satisfied, then the complex variable j will come into picture. Okay. So, please keep in mind that for the underdamped system dynamics, b square is less than 4a, and that result in the two type of variables lambda 1 and lambda 2 in the form of complex numbers given by gamma 1 plus j gamma 2 and gamma 1 minus j gamma 2. If I have forgotten that, let me again rewrite. Okay. The gammas are, yes, j's are there, it must be there, otherwise we get incorrect expressions. Okay. So, only when lambdas and gammas are taking this form, then only a, b and c can be expressed in these forms. Okay. That is very important. Further, a can be written in the form of the parameters of the dynamic model as lambda 1 plus lambda 2 can be expressed as minus b by a, lambda 1 lambda 2 by 1 upon a. Therefore, here you will get as this b can be further written as k by a 0. Okay. So, these things you should not confuse, because the b can be written either in terms of the constants of the transfer function model or in terms of the new variables we have introduced, the lambdas or the gammas. Now, since C x t 0 has to be 0 for a limit cycle condition, that means to induce limit cycle for obtaining sustained oscillatory output, this condition has to be met. So, when C x t 0 equal to 0, the initial state vector has to be given in some form as shown over here. Then x t 0 has to be given as x 0 1, which is a non-zero value with 0 element at the bottom. Okay. Why that is so? Since C is having the form 0 1, this is a vector having elements 0 and 1, then C x t 0 will be equal to 0 1 times x 0 1 and 0 is equal to 0 times x 0 1 plus 1 times 0 is equal to 0. So, for obtaining C x t 0 equal to 0, x t 0 has to be made available in this form. This point is very important. You cannot arbitrarily choose the form of x t 0. X t 0 must have some non-zero element in the upper and some 0 element. This must be 0 at the bottom, and the upper cannot be also 0. In that case, you do not get anything from the analytical expressions. Okay. So, the form of x t 0 is chosen corresponding to the set of the constants a, b and c. So, x t 0 will be given in the form of x 0 1 and 0. Please keep in mind, you must choose x t 0 in this form, otherwise the analysis will result in faulty expressions or erroneous expressions. Now, when a symmetrical or ideal relay is employed to conduct the relay test for obtaining sustained oscillatory output, then a typical output of this form can be obtained. Okay. Then we have got the time axis, and this is you have got different type of outputs. Okay. Outputs. What outputs we have shown here in this diagram? Here we have got the process output subjected to relay feedback. This is the process output. And what about this one? This is the relay output. So, corresponding to the symmetrical or ideal relay, what you have got? You have got some symmetrical process output and symmetrical relay output. Okay. So, the process output is now having different parameters, the peak amplitude given by the variable A p, which occurs at time t equal to T p, and the relay output has a delayed relay out. As you know, the process is subjected to delayed input. So, that way the delayed input or the relay output is given in this form. When this is the this occurs, the relay setting changes its value after time t equal to theta, and the half period of the output, is shown by capital T. So, I will use this variable T for half period of the output signal. Okay. So, the variables we have here are A p, the peak amplitude, half period of the output given by T, and all other parameters, H is the relay setting, and theta is the delay associated with the plant dynamics. Okay. And Tp is the time at which the peak amplitude of the output occurs. Okay. Now, we will go to the further analysis. The area of the process output over the half period. Please look at the half period. So, half period spans from time t equal to 0 to time t equal to capital T. So, this is our half period. Then what will be the area of the output signal? This area of the output signal, I can write an expression of the form limit from 0 to t y t dt. What is y t again? Y t equal to C x t. So, this can further be written as integration from 0 to t C x t dt. So, we can have expression for x t for different span of time. So, as you know, I can find from the waveform, for this part of the waveform, the corresponding output can be obtained using expression C x t, where x t can be given as, you know, if the output is like this is the output, half period of the output we will consider, and relay switching takes place here suppose, then in that case we will have two segments. One expression for this part of the output, which has got the state equation of the form x t is equal to e to the power a t x either 0 or t 0 x 0 plus a inverse e to the power a t minus I b h for the time 0 is less than equal to t is less than equal to theta. So, till time t equal to theta, this is equal to theta. Please see the way I have shown the theta. So, for this time we have got the state equation for that part of the output given by this. Then the output expression for the output will be simply y t equal to C x t. Okay. So, this is how the expression for output can be obtained, or indirectly speaking I can make use of x t in that expression to find the area. Which area? Now, this part of the area. What about the remaining part for this half period? Area for this part can be obtained provided we have got an expression for the state. Okay. And expression for the state can be given as x t is equal to e to the power a t minus theta x theta. Please keep in mind the change I am introducing here, minus a inverse. Why this minus sign is coming? The relay switching is taking place. The input or the relay output or the process input is going to be negative. Okay. Then minus a inverse e to the power a t minus theta minus I b h. So, this will be the expression for the time range theta is less than equal to t is less than equal to t. So, for this span from theta time till t, this is your till t. Okay. So, from time t equal to theta to time t equal to t, for this part of the output, the state equation is given by this. Okay. And once you get the expression for the state equation, the output expression can easily be obtained as y t equal to c x t simply. So, multiply c over here and you get the expression for output y t is equal to c e to the power a t minus theta x theta minus c a inverse e to the power a t minus theta minus I b h. So, use this y t and y t for different span for obtaining expression for the area. So, a y dash, a y area of the output signal or output over a half period of time denoted by a y dash is given by a y dash is equal to integration from 0 to t c x t dt is equal to integration from 0 to theta c x t dt plus integration from theta to t c x t dt, where please use correct expression for x t and x t for different time ranges. Okay. Then upon simplification, it is not difficult to get an expression of the form a y dash is equal to k times t minus 2 theta times h minus 2 k x 0 1. So, this detailed derivation I am not going to repeat here or give here. Obviously, if you substitute correct expression for x t and x t for different time ranges, you are going to get the expression for the output of the half period h a y dash is equal to this much. Okay. Now, we shall see the area of the input signal. Now, the area of the input signal can easily be obtained. How can you obtain the area? What is the input signal? Input signal is this one. Okay. So, then this input signal area of this part will be how much? Simply h times this span, okay, height and length. So, that way this part will have area h theta. Whatever the area of the bottom part of the output signal, this will be how much is this one? This span is nothing but your if this is t minus theta. So, not up to this one, this span is t minus theta. Therefore, this area, please do not consider, we are considering up to half period, the area for the half period. Okay, we will have two pulses, this upper one and this bottom one. Therefore, this area can be found further as the height is minus h and the span is t minus theta. So, the upper area is net area a u dash can be obtained h theta minus h times t minus theta. So, please simplify this one, h theta minus h t plus h theta. So, that gives you 2 h theta minus h t, and if you take h as common, 2 theta minus t times h. Now, I have got an expression in different form. Now, the area of the output signal or process input signal or relay output signal is given by t minus 2 theta times h or h times 2 theta minus t, only sign change is there. Why sign change is there? When the output is positive, when the system output or the sustained oscillatory output is positive, if you carefully observe the block diagram of relay control system, the input relay output or input to the system becomes negative. Therefore, we have to consider the negative of this one. I believe you are following what I mean by that. Let me go back to that structure. So, when this becomes positive, when y is positive, what will happen due to this negative feedback? So, relay will be subjected to negative input and the output of the relay will be negative. So, when y is positive, you are getting some positive area, you will get some negative area given by the relay output, and that is why the correct expression for the output corresponding to a y dash will be t minus 2 theta times h in place of 2 theta minus t times h. Okay. So, finally, allow me to write a u dash is equal to t minus 2 theta times h. Okay. So, this is how we get the areas of output and input signals over a half period of time. Now, what information we get from that? That can be used to get an expression of the form x 01 is equal to k times a u dash minus a y dash upon 2 k. Since you have got a u dash h t minus 2 theta h and a y dash is k times t minus 2 theta h minus 2 k x 01. So, a y dash is equal to, basically it is nothing but k times a u dash minus 2 k x 01, which upon simplification will give you 2 k x 01 is equal to a y dash minus k a u dash, and further it will give x 01 is equal to a y dash minus k a u dash upon 2 k. So, when why we are doing all these analysis? So, when a y dash and a u dash can be obtained from the output signals, then we can estimate x 01 conveniently, and this can be used to estimate, this expression can be used to estimate one parameter associated with the transfer function model. Now, I will go to other expressions which are presented outright. I am not repeating the detailed explanation or the expressions required to find the final expressions, or what I mean by this, already we have presented the derivations for these expressions in the form of A p is having, A p was earlier having minus plus k times h 2 minus then your h 1 plus h 2 times r 1 to the power lambda 1 minus lambda 2 times r 2 to the power minus lambda 2 lambda 1 minus lambda 2. If you have not forgotten, please keep in mind, already we have given some general expressions, or we have derived the general expressions for peak amplitude of the output signal for general second order plus date time transfer function models. So, when h 1 equal to h 2 is equal to h, then it is not difficult to get the same expression expressed in the form of A p is equal to k times h plus r 1 times lambda 1 r 1 to the power lambda 1 divided by lambda 1 minus lambda 2 times r 2 to the power minus lambda 2 divided by lambda 1 minus lambda 2. Okay. So, with the limiting values of lambda 3 tends to infinity and h 1 is equal to h 2 equal to h. Okay. It is possible to find the expression for the peak amplitude h given over here. Okay. And what are those r 1 and r 2 now corresponding to these limiting values? R 1 will be e to the power lambda 2 theta times x 01 lambda 2 plus h minus 2 h, and r 2 is equal to e to the power lambda 1 theta x 01 lambda 1 plus h minus 2 h, and corresponding T p expression for the T p, the time at which peak amplitude occurs, can be given as theta plus ln of r 1 upon r 2 by lambda 1 minus lambda 2. Now, these expressions will be used outright to find analytical expressions for underdamped second order plus dead time dynamics. Okay. So, here what assumptions you have to make? Lambda 3 tends to 0 and h 1 equal to h 2 equal to h. With those assumptions, the peak time can be expressed as T p is equal to theta plus 1 upon gamma 2. Where from gamma 2 came? Again you need to substitute lambda 1 is equal to gamma 1 plus j gamma 2 and lambda 2 is equal to gamma 1 minus j gamma 2. So, with these substitutions the general expressions we have obtained, we have found earlier can be extended to find expressions for the T p time at which the peak occurs as T p is equal to theta plus 1 upon gamma 2 tan inverse of e to the power gamma 1 t sin of gamma 2 t divided by 1 plus e to the power gamma 1 t cos gamma 2 t. Please do not fear, because these expression can easily be obtained from the general expressions we have derived for T p, A p and so on. Similarly, A p can be found to be of this form. It appears to be very difficult, but the bottom one is the important one for us. So, finally, the A p expression for A p can be like this, and the zero crossings will result in an expression for of this form. So, these are the three important expressions. These are the three important expressions for us. Those can be used to identify the parameters of the transfer function model. Now, how do we get 1, 2 and 3? Again I am repeating, when you substitute lambda 3 tends to 0, h 1 equal to h 2 equal to h, gamma 1 equal to lambda 1 equal to gamma 1 plus j gamma 2 and gamma 2 is equal to gamma 1 minus j gamma 2 in those powerful expressions we have derived earlier for general second order plus date time transfer function model, then we can easily get T p expression for T p, expression for A p and for the zero crossings as shown over here. Okay. So, please you can try and derive it, these are not difficult, only you need to substitute the limiting values. As I have told, only you need to substitute the limiting values in those expressions, and you do find this simpler 1, 2 and 3, those can be used for identification of underdamped second order plus date time transfer functions model. Okay. So, with this I will go to the simulation examples. Okay. What could be the identification procedure? How to identify the parameters of the transfer function model G s given by k dash e to the power minus theta s upon a dash s square plus b dash s plus c is equal to k e to the power minus theta s upon a s square plus b s plus 1. So, the transfer function model has got how many unknowns? 1, 2, 3, 4 unknowns, but we have derived 3 analytical expressions. We have derived 3 analytical expressions. Of course, we are making 2 more measurements, the areas of the output signal and the areas of the input signal. Now, to estimate k dash theta a and b, k dash theta a and b or a dash and a k dash theta a and b, or indirectly speaking c is also inherent in k dash. So, indirectly speaking you are measuring either k dash theta a dash b dash c or k theta a b. To estimate all those, one asymmetrical relay test might be required. Then you can make more measurements. In place of the peak amplitude, one peak amplitude, you will have 2 peak amplitudes and you will have more number of expressions which can be solved simultaneously to identify more number of unknowns associated with the transfer function. Or when a single symmetrical relay test is conducted, in that case you have to make measurements like the half period, the peak amplitude, area of the output signal and area of the input signal over a half period. And then assuming k dash to be known, it is possible to estimate all the parameters associated with the transfer function model. Okay. We will go to one simulation example now, because if you use this, I mean we are making, we have got 3 analytical expressions. Keep in mind, we have got 3 analytical expressions. What are those 3 analytical expressions? One is for TP, one is for the peak value AP, and another for the zero crossing, another for the zero crossing. So, we have got 3 analytical expressions, 1, 2 and 3, and when we make additional measurements like the areas, in that case it will be possible to estimate 4 unknowns, and we have got 4 unknowns in the transfer function model. What are those? K, theta, A and B. So, it is not difficult to estimate all the unknowns associated with the underdamped transfer function model with the measurements of AY dash, AU dash or the areas of the half period and T AP, okay, and T AP. Now, let us consider a non-minimum phase plus date time process given by, sorry, this is non-minimum phase, not non, consider an underdamped plus date time process model of this form. Then an ideal relay with age equal to 1 produces sustained oscillatory output giving the half period h 5.261 seconds and AP h 3.674. It is again unitless, okay, for the time being. Now, further the half areas of the half periods output signal AY dash is equal to 12.278 and area of the input signal over a half period over the same half period is AU dash is equal to 3.261. Then we can develop an expression involving the date time in the form of theta is equal to 0.5 of T minus AU dash upon H, because if you look at carefully the expression for AU dash is given by 2T minus theta times H. Okay. So, using that I can easily write an expression for theta, and since T is measured, AU dash is obtained or measured, then it is directly possible to obtain the estimation for the time delay theta. So, theta is found to be 1 or estimated to be 1. Similarly, using 2 analytical expressions now, A and B can be obtained. Okay. So, A and B are estimated to be 4 and 0.5. Therefore, the transfer function model we obtained for the underdamped system dynamics is found to be quite accurate, and the model is very much equal to the original system dynamics. This is how we see the efficacy of the expressions we have derived for estimating the dynamics of underdamped system. Okay. Now, let us go to a second example where we consider an integrating process also. A relay with again H 1 equal to H 2 equal to 1 produces the parameters T is equal to 9.471 seconds and AP is this much, and using the set of analytical expressions I have derived, it is possible to identify the integrating process model also, identify the integrating process dynamics, whose model is given by now GMS is equal to e to the power minus 1.5 s upon s times 5.001 s plus 1. So, the accuracy is very high to within 10 to the power minus 4. Okay. So, we see that the applicability of identification method is not restricted for only underdamped processes, it can be made applicable for other type of processes as well. Let me summarize the lecture. So, a set of equations are presented for identification of underdamped process dynamics, and it is found that the identification technique can also be extended for other type of processes. Now, model parameters can be estimated using the 3 measurements from the symmetrical limit cycle output. actually not 3, we have to make 4 measurements, because those measurements could be T half period, peak amplitude and areas A y dash and A u dash. So, using the 4 measurements actually it is possible to estimate all the 4 unknowns or at least 3 unknowns associated with the transfer function model. Now, how the identification technique can be used for identification of integrating or other type of process dynamics, as I have already explained. Now, with proper choice of C, the parameter C associated with the underdamped second order plus dead time transfer function model, with proper choices of C, it is possible to identify either stable, unstable and integrating process dynamics. Okay. So, proper choice of C is required, proper choices of C is to be used. Now, what is the limitation of this identification technique? This identification, very often you may need to find the k dash associated with the process model by some other method. So, k dash may be found by some other technique. So, accurate estimation or accurate information about the steady state gain associated with the underdamped system model is necessary. Okay. So, care must be taken to find k dash accurately, then only the set of analytical expressions can be solved easily and correctly. Thank you.